So here's a motivational example for another trig integral. Let's say we wanted to integrate tangent squared times cosine squared, theta d theta. The first thing that I want to do is see if any trig substitution instantly pops to mind. And in this case, then secant squared, we could use some of the techniques that we talked about before, but it's not, it's a cosine. So my next go-to move is to actually break these down into their composite parts. That tangent squared is actually sine squared divided by cosine squared. And then I'm multiplying that by cosine sine squared over 1, I suppose. And this, I actually get a nice cancellation. But I can cancel each of those factors, and I see that this is just the same thing as the integral of sine squared d theta. So I simplified just using trig identities and not calculus. But the problem is, now that I have this is something that's very difficult to integrate. I debated going through, and maybe I could add that as a addendum in additional exercises, but it's really tedious. It's very cumbersome, and I think that there are certain types of trig integrals that are really interesting and valuable to be able to work through to motivate working with U substitutions, but this is a particular case where it's not as interesting and not as motivating. So instead, this is something that I would want you to either compute using a computer algebra system, or you could compute using a table that's provided in our text. And after some internal debate, I've decided that this text, sorry, I'm pulling it up from our book, maybe I'll get sued for copyright infringement, so don't share this, but this is a table of different trigonometric integrals. Notice most of them are written with variable, so if this were sine to the fourth, I could look up on this table how to be able to solve it. The original integral, tangent squared times cosine squared, isn't going to be listed anywhere here on this table, that you're going to have to break it down as far as you can in terms of sines and cosines, or maybe tangents, cotangents, and secants. But in this case, because this is a common one, they give you an identity. You'll have to use actually a double angle identity to be able to solve this. And I'm going to provide you in this table the fact that this integral is given by this particular value. In this case, I'm not using the variable x, I'm using the variable theta. So it becomes theta over 2 minus the sine of 2 theta over 4 plus c. And this is a mathematically equivalent one using a slightly different half-angle identity. So the reason why I want to bring this up is because sometimes going through lots of messy maneuvering to try to solve these integrals isn't worth it, and it's more valuable to just look it up in a table or to use a computer algebra system. And I will provide that table for you when you work through your exams or quizzes. If the table is there, it means it's unlikely I would give you something this simple that you would be able to simply look up the solution.